All right, it is time to begin. Welcome to Co-21C. I see many familiar faces, but not all familiar faces. So welcome to those who I've seen before. Welcome to those who are new to class. We'll go over the class logistical material briefly. There's pretty much one thing you need to know, and that's about it. So for those of you that are registered for the class, meaning you signed up with a CRN number, which I hate saying because the CRN stands for course registration number. If you sign up with a CRN, you have to come. For those of you that are not signed up with a CRN, meaning you emailed me or filled out a Google form, you should come, but you don't have to come. That's kind of it. So if you are registered for a unit and you want to get that unit, you have to come at least like 70% of the time because we have to grade you in some way because we're giving you a unit. Other than that, that's kind of it. So if attendance is going to be an issue for you and you don't need a unit, you could drop the class and get added back to campus and have all the same access to all the same materials that people enrolled in the class have. But if you do need one unit to be full-time with 12 units, then please come. Everyone should come, right? But if you have to come, please come. That's kind of it. Please don't email me about it. I get so many emails like mid-quarter, James, I see I'm failing the class. I'm like, you're not enrolled. You're not enrolled. So please don't email me about it. I try to make it very clear. It's the only thing that bothers me, really. That's not true. Lots of things bother me, but it's the only thing about teaching this class that occasionally bothers me. I'm like, oh my God, they keep emailing me. Okay. So that said, we'll look over this stuff real briefly here, and then we'll get started talking about some sequences. So let's see. You all know the material about where we're meeting because you're here. As far as getting a hold of me, email is best. You can also come by my office. You can also come to my office hours, which are listed right here. Let's take a look. There they are. Mondays and Wednesdays, 11 to 12 in the drop-in in Shields Library. Tuesdays, Thursdays from 1:40 to 4, also in drop-in. And then Monday, Wednesday, Friday, right before this class in CADS, the Center for African Diaspora Student Success over in South Silo. So it's very close. So if those office hours work for you, they might make sense because it's close to this class. And then FYI, so the office hours in CAD start next Monday. The office hours in drop-in start the Monday after that. Drop-in tutoring starts actually Sunday, October 5th from 3 to 7, and drop-in tutoring is Sundays from 3 to 7, and Mondays through Thursdays from 10 to 5. Also, you're welcome to ask questions, obviously. Hopefully it's obvious, but you're always welcome to ask questions if you got them. My name is James, by the way, because I didn't say that. Please just call me James. If you cannot do that, I understand. You can call me Mr. Parmenter, Mr. P, or teacher, or professor. I'm not a professor. Whatever works. But James is best because that's my name and I like it. What else here? Let's see. Grading. I mean, yeah. There's all the stuff there about what I just said, but really it's like if you're enrolled, come to class. If you're not enrolled, still come to class, but you don't have to. Also, to that end, I am recording class on Zoom. I will post the recordings of each class same day, typically, as well as whatever class notes I end up writing over here. So that is always accessible to you. I don't know what to say. So if you do come to class, which I would encourage, I will ask you all to fill out the sign-in sheet, put your name on there. If your name isn't on there already, just write it down below or on the back, because part of my job is keeping track of the number of students I serve. So this counts as that. So please do sign in there if you come to class. If you don't come in person, I do ask that if you watch the video later to attend class, not that but which doesn't count if you're enrolled, because I feel like you should come if you're enrolled. Fill out this form here. And I'll put that link to this form like everywhere. So if you're not attending in person, which obviously you all are, but if later on, like, I don't want to come to class today, but I still want to watch the video later, it would really be helping me out personally and our department out in general if you fill out this attendance form whenever you watch the class video for the first time. It's pretty easy. Name, email, student ID number. Really, the only really important part is the student ID number and the class and the actual correct date. So yeah. What did I write here? What did I write here? Oh, yeah. And you should put in the date for the day of the class met, not the day, and which the date will be on the video. The day of the class met, not the day you're watching it. That'll help me out if you do that, please. Pretty please. What else do we have to say here? Well, so many words. Um, yeah, there's no makeup for absences. So if you're enrolled, you do need to come in person. Also, it's better if more people come just because like when you get to a class when only like 3 or 4 people are showing up, it just feels like not everyone's having a good time. It feels very sparse. So come, enjoy math. I imagine most of you probably have to take 21D as well at some point, because usually if you, not all of you, but many of you will have to take 21D and 22A and 22B. I don't know where I was going with this, other than you have to learn the material to take the next material. We don't have a co-class for 21D typically, because there's just so many other classes that require support. That said, just thinking towards the future, I'm usually pretty good the first 2/3 of 21D, the last third of it, it's been too long. Grant is also pretty typically helpful with 21D. So just looking towards the next quarter. 22A, on the other hand, I would love to talk about. So you can take 22A, come see me, or Casey. Casey does a workshop usually every quarter for 22A and 22B. He's the man, and I'm the next man. What else? Yeah, we'll do examples, accommodations. If you need an accommodation, please let me know. Although this class typically doesn't really necessitate that because there's no homework, there's no exams. You can record if you want to, although I'm also recording it. So whatever you need, I'm happy to do, but there probably isn't a lot that is needed. What else? This class is worth 1 workload unit if you're enrolled. If you really don't want to be enrolled, that's totally fine. Just drop the class, email me, I'll add you back in. It's easy. As far as getting math help, my office hours, there's also, I mean, most of you, I think most of you have been students here already, but if you haven't, you can also get help in drop-in tutoring, which I mentioned already. There's also something here. You can also like make an appointment to have a tutoring session with a student tutor, I think. At this point, I would say though, you're probably better off talking to each other. Like, not that student tutors aren't good and helpful, but you all have been taking math for a while now at this point, so you are each other's best resources after, no, really, you're each other's best resources. So work together. That's how you're really going to learn it. What else do we have here? Sure. And then, so this is the homepage right now. I'll change it pretty quickly to the modules, which is where anything useful will actually be. Let me do the student view here for a second. So there's some useful links here. The link to the attendance form, the link to the Zoom if you're not coming to class in person, my office hours, my playlist on YouTube from past times I've taught the class, and also the current videos will be there as well. My website is trash. You don't need to go to it. Grant's website is very useful. You should check it out. Kuba's old 21C website also has lots of useful materials on it if you're looking for extra study materials. And then there's the math department syllabus for the class in case you're curious about looking at what's coming up next. Like I printed it out, have it right here because I'm like, oh, what's next? Oh, series, sequences, all that kind of stuff. And then there's some review material. If it's been a while, you should definitely make sure you still know how to take derivatives and integrals. Those are important things you still have to be able to do for pretty much any math class you're ever going to take. Maybe not entirely, any lower division math class you're ever going to take. You probably at some point will have to take a derivative or an integral of some shape, way, I don't know, words, yeah. And then there's some handouts for series stuff, which we will get to. Maybe, probably not today. And then there's some old problem solving handouts that are posted here, and the solutions are posted on Grant's website. If you're looking for extra work, also a good resource. There's lots of them. I think they're better labeled on Grant's website, though. Let's take a look. Can I take a look? Maybe. Let's see here. There we go. Okay. So if you start here, there's like lots of handouts about this material, more like lecture notes. But then if you scroll all the way down, there's problem sets and solutions. So that could be another place if you're looking for problems you want to work on yourself before seeing the answer, but then also have the solutions available. You check the work out. That's a really useful resource. Oh, look, someone joined us via Zoom. Welcome to the person joining us via Zoom. Cool. Let's see, what else? I think that might be just about everything, but let's take a quick look here. Scrolling down. Yep. That's the end. Yeah. And then I'll probably post, so also in the modules, I will post the class video, the lecture notes, and probably like practice exams at some point. There's like 3 different people teaching this class. There's Luli and Carlson and someone else who I should know the name of, but I forgot. Oh, Lee. Lee famously does not give practice exams. Maybe not famously, infamously. Um, to me anyway, because I feel like I've taught a lot of his co-classes. I'm like, no practice exams ever. So I'll try to come up with something for you all before you have exams. Hopefully none of them have added me to their Canvas yet, so I have no idea what they're doing in the classes. I've sent them all emails. Hopefully they'll eventually see them and add me. All right. So before we start doing any math, any questions about anything I've said? Sure. What was this? Am I looking over there? I can see it right here. Something else. Oh yeah. Class this Friday is canceled. Yeah, I have a funeral to go to, which is not that sad because my grandma lived to 90, so I think she did all right. But yeah, I won't be here, so don't come to class on Friday. I won't be here, and we'll meet on Monday. Any questions at all before we start with the math? Actually, I should ask you all a question. So, did anyone's class cover any math, or did you all just talk about syllabi today? What did you guys talk about? Okay, cool. And whose class were you in? How about is anyone in Carlson's class? What did you guys do today? Cool. I'm sorry. Usually that's something we don't really, I mean, you can, but all right, sure. Yeah, I see. Yeah, all right. And who's the other instructor? Lee, oh, that's right. Yeah. And what did he do in class today? Or have you had class yet?
Sequences and the delta epsilon.
So what's the delta epsilon stuff that's going on? Like, okay. Okay. I guess, yeah, some people like to get into the nuts and bolts of it. Well, if we have to do it, we'll have to do it. So, all right. I guess we'll start talking about sequences, which aren't that bad. Well, let's see here. So Co-21C, today is the 24th. Maybe you want to see what I'm writing? Sure. Let's do that. As usual, if I get off the page somehow or you can't see what I'm writing, or if something I'm writing is hard to read because my penmanship is not excellent, please just let me know. And feel free to ask questions along the way. Let's take a look at the lighting situation. Let's see here. This is not the best. It's typical.
So fast.
That better? That's better, right? Yeah. The other emotion today, you had to turn off all the lights, which I don't love, but we'll do. All right, so sequences. AKA lists of numbers. So often when we talk about sequences, we talk about them as kind of a formula definition. So for example, I could give you the sequence A sub n is equal to 3n over n plus 1. Frequently, you're not given a starting place. If you're not, we usually assume you start at n equals 1 or n equals 0. Usually n equals 1 unless your teacher is different. But again, if they want to be specific, they will be. They'll say start at n equals 0. but you're usually starting with the non-negative or positive integers. But it is just integers. So unlike a function, where functions usually have a domain of every possible input, these functions, because they are functions, which are sequences, the only inputs are usually the positive integers. So we'd say, cool, a sub 1 is going to be 3 times 1 over 1 plus 1. And then our a sub 2 is going to be 3 times 2 over 2 plus 1. And the next one's going to be 9 over 4. And so on and so on and so on. And this is a pretty typical way of writing out the list. You just write the first few of them and then you say dot, dot, dot. Someone could ask us, what's a sub 20? And we would just substitute in 20 for n. So we'd have 3 times 20 over 20 plus 1, which is 60 over 21. And although I certainly, in general, would prefer to reduce that fraction because that's just my nature, it's usually not in your best interest unless someone's asking you to. Because what we're often going to do is we're kind of going to go the other way and start with a pattern, and reducing the fractions makes it harder to see the patterns that are there. So usually you don't want to reduce your fractions. The question that we often ask, though, is, does this sequence converge? Really, we should say, does the sequence converge or diverge? Because those are the only options. It either converges, meaning the list of numbers gets closer and closer to one specific real number, or it doesn't. In this case, actually in all cases, what that's going to typically mean is finding the limit as your input n approaches infinity. So to answer this question, we take the limit as n goes to infinity of our sequence, 3n over n plus 1. And this is probably where some people started talking about delta epsilon stuff, which we'll see about that. I would say generally, when you're finding these limits, you should use whatever tools you have at your disposal from 21A typically. In this case, we just have a rational expression. Highest power on the top and bottom is the same. We know the limit's going to be 3 divided by 1. The numbers get closer and closer to 3. And you can kind of see that over here, in fact, right? The 20th term, 60 over 21, is pretty close to 3. If it was 60 over 20, it would be exactly 3. And if you go even further out, if you go to the 999th term, just to make the math easier, you're going to get 3 times 999, which is 2,997 divided by 1,000. Yeah, that's pretty close to 3. So we can see that as we go further and further and further out, the values get closer and closer to 3. I'm debating internally, like, do I really want to talk about the delta epsilons? Because the problem with the delta epsilon stuff here is that, like, it's just kind of gross. And here's the real problem. I haven't thought about it enough to say it clearly, is the real issue for me. I'm like, oh, I wasn't planning on doing that today, and I haven't really thought about that. So we'll save that till Monday. But for now, we're just taking limits kind of the nice way we're used to taking limits. And all the limit rules apply, meaning you can use L'Hopital's rule. It's usually very available, with some exceptions. One exception, really, which we'll talk about eventually. So let's look at some other examples, though. So, numbering things. I try to number things. I'm never good at it. So let's look at this sequence. Let's say Bn is equal to 3n squared divided by n plus 1. I personally don't find a lot of value in writing out terms if I'm given the formula already. Like, we could write out terms. Our list is going to be 3 over 2. And then if I plug in 2, I get 3 times 4, which is 12 over 3. If I plug in 3, I get 27 over 4, right? But to me, it feels like an exercise in futility, maybe. I just don't see the point in writing out the terms other than showing that I know how to plug in numbers to a function. But sometimes you'll be asked to write out the first 5 terms because, I don't know, they want you to do something with it. To know what you're supposed to do with the sequence is write a list of numbers. But the more interesting question is, does this converge or diverge? So we again take the limit as n goes to infinity of our formula for our sequence. And that's always the thing we're doing if we're asking if it converges or diverges for a sequence. We're taking the limit as n goes to infinity, or as whatever the index is called goes to infinity. Here, our limits, well, how do I want to say this the right way? Let's just find the limit. So you could use one of the rules you have from calculus, or I would say if you don't remember the rules, the thing we do when you have a rational expression like this is divide everything by the highest power of your variable that occurs in the denominator. So here I would divide every term by n to the first power. If I do that, look at what I get. If the limit then goes to infinity, I'm going to write out all the things. Dividing the top by n, I'm dividing the bottom by n. If I simplify, I have the limit as n goes to infinity of 3n divided by 1 plus 1 over n. 1 over n goes to 0 as n gets really big, but 3 times n goes to infinity. So I'm going to get infinity over 1 plus 0, which is infinity. Okay, so here's a question that is meant to be kind of tricky, or at least meant to make you think. Does this limit exist? And the answer is no. The limit does not exist. Why not? What number is this limit getting close to? Infinity is not a number, right? You can't look at a graph or whatever and say this graph is getting closer to some particular number. What we can say is it's getting larger and larger and larger. But the faster way of saying that is limit is infinity. Right? So when we say limit is infinity, we're saying two things at once. We're saying this sequence, the terms get bigger and bigger and bigger and bigger and bigger. Said two things at once. What was the other thing? And the limit doesn't exist. So that's what we mean when we say the limit is infinity or negative infinity. The limit does not exist. And also, I'm telling you a little bit more. The terms happen to get larger and larger and larger as you go further and further out. So here, we would say that this sequence, 3n squared over n plus 1, diverges. It is not getting close to one and only one particular number. Yeah.
And what do you mean by, you're saying that it's both does not exist and it diverges?
Correct. So, and I'll say, so when you're talking about sequences, if the limit does not exist, then we also say that the sequence diverges. And there's a couple of different ways a limit cannot exist, aka there's a couple of different ways a sequence can diverge. One way to diverge is by all the terms getting larger and larger and larger. But sometimes the terms just keep bouncing back and forth between something. For example, I could say, here's an annoying one. My sequence is, cosine of pi n. This is the annoying way of writing what I'm actually going to write in a minute. But if we start plugging in values for n, let's see. So for n equals 1, I get cosine of pi, which is negative 1. For n equals 2, I get cosine of 2 pi, which is positive 1. And then for n equals 3, 3 pi, cosine 3 pi is negative 1 again. And we just keep bouncing back and forth between the right side of the unit circle where cosine is equal to 1 and the left side of the unit circle where cosine is equal to negative 1. But we're not getting closer and closer to any particular number, right? This goes on forever and ever and ever and ever and ever. And so we'd say, if you try to figure out if it converges or diverges, the limit as n goes to infinity of cosine of pi n, the only thing you can really say here is it does not exist, right? Not that it's infinity or negative infinity, because it's not. It just doesn't exist. And since the limit of the sequence doesn't exist, the sequence itself diverges. On the other hand, in our first example, when the limit existed, the sequence converged, and it converged to the limit value, which I didn't probably write, but I'm saying now. To add on to that example, actually, so I'll point out an equivalent way of writing this sequence, which is probably more likely to be seen, is you could also write this as a sub n equal to -1 to the nth power. And if n is 1, you get -1. If n is 2, you get +1, and so on and so on and so on. But sometimes people try to do tricky things and write it this way to kind of hide the fact that you have something that's alternating signs like this. And we will see a lot of alternating things in our future. Speaking of alternating things, let's look at another example. Let's look at, say, b sub n equal to -1 to the n plus 1 multiplied by 2n over n plus 3. So if we start writing out terms, because again, just kind of think about what's happening here. If I start with n equal to 1, my first term is going to be -1 to the 1 plus 1, which is -1 squared, which is positive. And then I'm going to have 2 over 4. So I'm going to have 2 over 4. But then we're going to alternate signs, right? Because every time we increase the power by 1, we're going to have an odd or an even, which is going to translate to a -1 or a +1. So our next term is going to be negative, and then if n is 2, I'm going to get 4 over 5. And then positive 6 over 6. And then negative 8 over 7. And then let's do one more. Positive 10 over 8. In fact, you can kind of, I mean, not surprisingly, I'm really just looking at the pattern, actually. I'm not actually plugging in n equals 5 here, although it's not hard. I know that the top is always going to increase by 2, so my next one is 10, and the bottom is increasing by 1. So the next term is going to be negative 12 over 9. The next one's going to be positive 14 over 10, etc. So how do we determine if this one is convergent or divergent? Well, it's kind of hard to think about taking this limit. What I would prefer to do is the following. I'm going to look at the limit as n goes to infinity of the non-alternating sequence, the 2n over n plus 3. And everyone should show me on their fingers, what's that limit equal to? I see the few, I'd like to see more fingers. So I'll remind you, this is 2n to the first over 1n to the first plus 3. Oh yeah. So right, this thing happens a lot. You should, I know it's always like, it feels like the easiest example is almost the hardest one to do. Like if I gave you all this limit, the limit as x goes, this pen is dying, as x goes to infinity of say 3x squared plus 5 over 7x squared minus 2x plus 1, I think everyone can tell me pretty quickly the answer is what fraction? Right, 3/7, because you're used to seeing it this way. It's the same thing here. It's just a lesser power that we're not writing and a different variable, but it's still the same idea. This limit's going to be 2 over 1, which is 2. But the problem here is that in this example, if n is odd, the limit is positive 2. And if n is even, the limit is negative 2. So we're bouncing back and forth between a number that's close to positive 2 and a number that's close to negative 2, and the positive 2 and the negative 2, and the getting closer and closer to each one. But as we keep going further and further out, we're not getting close to one and only one specific number. So the limit doesn't exist. So the limit as n goes to infinity of -1 to the n plus 1 times 2n over n plus 3 does not exist. Here's something I think is an interesting fact. An alternating sequence, if it converges, can only converge to one number. 0. That's the only way, that's the only number that both positive numbers and negative numbers can get closer and closer to at the same time. So just as an aside here, an example of something like a sub n equal to -1 to the n times 2n plus 1 over n squared plus 5 that will converge to 0 because the non-alternating part here, the 2n plus 1 over n squared plus 5, the limit of that part is going to be 0. And the way we can see that without doing all the work is by seeing that the degree on top is less than the degree on the bottom. This is 2 times n to the first over 1 times n squared. I don't really care about the smaller powers here. This is gonna, if you think about this, the denominator is getting larger much faster than the numerator. This fraction is getting smaller and smaller and smaller. Or you could do the work, right? Or you could use L'Hopital's rule. Right? There's lots of options here. If we let's use L'Hopital's rule. Not that it's necessary here, but using L'Hopital's rule, the derivative of the top is 2, the derivative of the bottom is 2n, and as n goes to infinity, 2 over 2n goes to 0. Which means you have every other term being positive and getting closer to 0, and every other term being negative and getting closer to 0, and they're both getting closer and closer to 0, so the limit's 0. So this sequence converges to 0. And I'll say it again because I think it's important. If an alternating sequence converges, it has to converge to 0. Yeah, no, that's true. I was trying to think about some weird counter case, but no, that's not really, it's technically not alternating. So if an alternating sequence converges, it has to converge to 0. You can make up a pseudo alternating sequence where you like took the same thing and just like added 5 at the end. And then you have terms that like we're bouncing back and forth between like bigger than 5 and smaller than 5, bigger than 5 and smaller than 5, and it converges to 5. But it's technically not alternating then, because to be alternating, you have to go positive, negative, positive, negative, positive, negative. So wouldn't really be, it would look alternating, but it wouldn't be alternating. Questions? It's okay if you don't have it. I see you discussing. All right, let's see what else have we got here. And you're always welcome to take pictures. I will also remind you, I will post the lecture notes, so you don't have to take pictures, but I know it's nice to have them there. Let's say we have something like a sub n equal to n cubed over 3 to the nth power. And this is a time where I think your intuition is probably going to be super helpful here. Which of those functions do we know gets bigger faster? The polynomial n cubed or the exponential 3 to the n? The exponential. Exponentials are always going to outpace polynomials. So being raised to a variable power is going to overcome being raised to a straight number power. But we can also write out terms. And actually, if you write out terms, you can kind of deceive yourself if you don't write enough terms. Our first term is going to be, oh yeah, question.
What is n to the n?
I don't know if there's a name for that actually.
But I didn't understand. I think he said super, or did he?
Oh, if it's probably a name after a person, but yeah, I don't know. That's a good question. I'm curious. N to the n is not, but it's definitely not exponential or polynomial because you don't have a constant base or a constant power. N to the n is also annoying, but we'll look at that in a minute here. So we start writing out terms: 1 to the third over 3 to the 1, and then 2 to the third over 3 to the 2, and then 3 to the third over 3 to the third. So every time we write one more term, it looks like the denominator is getting much bigger than the numerator, right? The numerator here is going to be 4 to the third, which is 64. The denominator is going to be 3 to the fourth, which is 81. So, right, this one is smaller than 1, equal to 1, smaller than 1. The next one, 5 to the third, which is 125, over 3 to the fifth, which is 243. Right, we're going back the other direction. The denominator is getting much larger than the numerator is. So the next one would be, 6 to the third over 3 to the sixth, whatever that is. Small. But writing out enough numbers isn't enough to show that the limit is what we think it is, right? To actually show that this sequence converges to 0, we have to actually take the limit. So limit as n goes to infinity of n cubed over 3 to the n. And this is an example where we do kind of have to use L'Hopital's rule. There's not really a lot of other options here. So using L'Hopital's rule, You take the derivative of the top, which is easy, 3n squared. And I want you all to write down the derivative of the bottom. Yeah, it's been a minute. Remember how I said we need to know derivatives? Because L'Hopital's rule? I didn't say because L'Hopital, but this is definitely one of the reasons why you have to know your derivatives, because L'Hopital's rule is often getting used for showing a sequence or a series converges or diverges, because you're taking a lot of limits and you often have to use L'Hopital's rule. The derivative of 3 to the n, well, the derivative of e to the n is e to the n. The derivative of 3 to the n is 3 to the n times the natural log of 3. Still, I should have said more words here. Why we're using L'Hopital's rule in the first place? Because we have the right type of form. If you tried to plug in infinity, the numerator would be getting infinitely large, the denominator would be getting infinitely large. We have the right type of indeterminate form, infinity over infinity, or 0 over 0, but usually infinity over infinity. So we can use L'Hopital's rule. But then we still have it here. The numerator is still infinitely large, the denominator is still getting infinitely large, so we do it again. The derivative of the top is 6n. The derivative of the bottom, the natural log of 3 is a constant. It's just going to hang out. The derivative of 3 to the n is again 3 to the n times natural log of 3. And then we have the other natural log of 3 that's still there. And then we have to do it one more time. And I think we can see what's going to happen here. The limit as n goes to infinity. The derivative of 6n is just 6. The derivative of 3 to the n is again 3 to the n times natural log of 3. And then we have those other two natural log of 3's that are already there. And now we have something that is constant on the top and the denominator that's getting infinitely large. So we're getting 6 over infinity, aka we're getting something that's getting closer and closer to 0. So this sequence, a sub n equal to n cubed over 3 to the n, does converge to 0. Now, I don't think you need to write these words here. It is perfectly sufficient, in my opinion, to write the limit as n goes to infinity of n cubed over 3 to the n is equal to 0, which we've already done. But I'm just trying to emphasize here the fact that, oh yeah, this means we say it converges to 0.
How did you know immediately that we have to use that again?
That's a good question.
Or like you said something like we have to use this.
Right, well, because I think it's more from 21A, like when we encountered, like in 21A, you encounter limits like this in like the L'Hopital's rule section, where like we don't really have a way of dealing with a limit like this without L'Hopital's rule. Like there's not really any like factoring I can do, or dividing everything by n to the third wouldn't make a difference at all. Yeah, also there's kind of, yeah, but you're right. I don't have a good explanation as to how I knew to use L'Hopital's rule other than from the experience of 21A, really. Now, here is a kind of counter example to that, or a situation where we're not so happy about it. So let's look at this next one. The numbers fell apart immediately. Let's look at b sub n equal to n factorial over 4 to the n power. I would point out also in this previous example, right, we really saw that this sequence, I know I just took it was n factorial over 4 to the n. This sequence converged to 0, meaning the denominator outpaced the numerator. And what you can kind of take away from this is that any exponential, like 3 to the n, 2 to the n, or 5 to the n, or anything to the nth power like that, as long as the base is larger than 1, is going to overcome any polynomial. So I would just point out generally here, b to the n is going to overcome n to some power, as long as b is larger than 1, and your power should also be larger than 1. So you can have something like 1.1 to the nth power is eventually going to over like n to the 100th power. It'll take a while, but eventually the exponential thing always wins the power of the question of who is bigger eventually. But then we have factorials. And the disappointing thing about factorials is we cannot use L'Hopital's rule. because we can't take the derivative of n factorial. It's just not a thing. It's not a nice continuous function. It doesn't have a nice derivative. There probably is. In the context of this class, like I'm saying that, so you're right. I'm saying things that are probably not 100% actually true. And n factorial might actually have a more general definition. But when we think about the n factorial function, we typically think about n only being an integer, and n factorial is defined to be equal to n multiplied by every integer less than it all the way down to 1. A couple things to know about this. It's probably not super important to know this, but I'm going to say it anyway. 0 factorial is defined to be equal to 1. Which I know is kind of weird. It's kind of like how 3 to the 0th is equal to 1. There are other formulas that we know about. So sure. Let's quick aside here. Sorry. So why is 2 to the 0 equal to 1? I know it's a dumb question. The answer is because it needs to be. Why does it need to be? Because of other rules, specifically the additive law of exponents, right? You know this thing that b to the x times b to the y. What do you do with the exponents? You add them. Well, if we want that to be true, cool, then this has to be true. Because if you multiply 2 to the third by 2 to the 0, what do you do with those powers? You add them. 3 plus 0 is 3. So if 2 to the third times 2 to the 0 is equal to 2 to the third, 2 to the 0 has no choice but to be equal to 1. In a similar way, there's a function called the choose function that helps counter the number of ways of picking so many things from so many things. It's kind of interesting, comes up in stats a lot. Also comes up in the binomial expansion, Pascal's triangle, all over the place. But that's why we need this to be true, because otherwise other formulas that are true in general would fall apart. And it's kind of a too brief explanation, but if you are interested to know more about it, come ask me about Pascal's triangle sometime. I would love to talk about it. Anyway, back to this. We can't use L'Hopital's rule to answer the question, does this converge or diverge? So we're still going to start by saying, well, what's the limit as n goes to infinity of n factorial over 4 to the nth power? Good question. Well, let's look at some terms. The first term, not too bad. 1 factorial over 4 to the 1, which is 1/4. The second term, 2 factorial over 4 squared, which I'm going to think about as 2 over 4 times 1 over 4. So it got smaller actually, right? I multiplied my previous thing by 1/2, it got smaller. I don't really need to say what it is, but it's 2/4 times the previous term. A sub 3 is going to be 3 factorial over 4 cubed, which we're going to think of as 3 times 2 times 1 over 4 times 4 times 4. This part here is your previous term, A2. So this is 3/4 of A2. Again, smaller than the previous term. So A sub 1 is something. A sub 2 is smaller than A sub 1. A sub 3 is smaller than A sub 2, which is smaller than A sub 1. And if you didn't do your due diligence and stopped here, you might incorrectly convince yourself that all the terms are getting smaller. But they're not. Because if we keep going, our next term, A sub 4, which is 4 factorial over 4 to the 4th, is 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4, which is, there's your previous term, A3, multiplied by 1. So it didn't get smaller or bigger, it stayed the same. And then after that, the terms are going to start getting larger, right? Our fifth term here is going to be 5 factorial over 4 to the 5th, which is 5 times 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4 times 4. And there's your previous term in parentheses. So this is 5/4 times A sub 4, which is bigger than A sub 4. And my terms are going to keep getting larger and larger and larger, right? My next term, A sub 6, is going to be 6/4 times A sub 5. And my a sub 7 is going to be 7/4 times a sub 6, and so on and so on and so on. So if we keep multiplying by a number that's getting larger and larger and larger forever, it's going to get infinitely large. But there isn't really a good way to like show this. This is the argument for this. So we can say, cool, this shows that the limit as n goes to infinity of n factorial over 4 to the n gets infinitely large. Now, I'm not going to write it this time, but we know that this means that our sequence diverges because the limit does not exist. I'm going to write it. Liar. Times it. Okay. Also, sometimes I lose track of time. Don't let me go. Like if it's 4 o'clock, be like, hey Jane, or if it's 3:59 or whatever. Yeah. If it's close enough to class ending, let me know because I might lose track of time. This clock is correct though, so I should be fine. Let's look at one more. Oh, so I'm just going to add to our list here of things. I'm going to point out that, sure, polynomials are outpaced by exponentials, but those are outpaced by factorials. And then just to add to the list, factorials do get outpaced by whatever we call this thing. So, yeah. We can go the other way too. Polynomials certainly outpace. Actually, I'm something else at first, but yes, a root, it's like the pth root of n, or n to the 1 over p power, and then those. Well, what grows slower than those? Logarithms. Logs are kind of the slowest thing we got, or a log of a log. Okay, and here's the last one I have for you today, which is kind of my favorite one, which you've hopefully seen before. If you haven't, now you will have. So let's look at a sub n equal to 1 plus 1 over n to the nth power. Does this converge or diverge? Good question. Well, let's take the limit. So limit as n goes to infinity of 1 plus 1 over n to the nth power. If we plug it in, we get 1 plus 0, which is 1, to the infinitieth power. Now, be careful when you look at this, because we don't really have 1 to the infinity. Just like we don't really have infinity over infinity or 0 over 0 anytime. We have things that are close to 0 over things that are close to 0, or things that are really big over things that are really big. Or here we have something that is really close to 1, but still a bit bigger than 1, multiplied by itself a lot of times. It's not 1, because that number isn't 1. That number is a little bit bigger than 1. Here's the problem. If you do something like, say, let's say n was equal to 100. If you do 1 plus 1 over 100 to the 100th power, it's about 2.7. I do have a calculator too, but it's going to be 2.7-ish. Because you're multiplying 1.01 by itself 100 times. And eventually the largeness of the power overcomes the smallness of the part you're adding on, but not fully. So let's actually do this limit. If we want to find this limit, we're going to, instead of writing it as 1 plus 1 over n to the n, we're going to write it as the limit as n goes to infinity of e to the natural log of 1 plus 1 over n to the n. And then we're going to rewrite it as the limit as n goes to infinity of e to the n times the natural log of 1 plus 1 over n. And then finally, we're going to rewrite it as the limit as n goes to infinity of e to the natural log of 1 plus 1 over n divided by 1 over n. And now my exponent here is the kind of thing you can use L'Hopital's rule on, because n is going to infinity, 1 over n is going to 0, 1 plus 0 is 1, natural log of 1 is 0, over 0. So this exponent is a 0 over 0 type, and if we use L'Hopital's rule, we have the limit as n goes to infinity of e to the derivative of the top, the derivative of the natural logarithm stuff is 1 over the stuff times the derivative of 1 over n, which is negative 1 over n squared, divided by the derivative of 1 over n, which is also negative 1 over n squared. The negative 1 over n squareds cancel. You're left with I should just take it. You're left with the limit as n goes to infinity of e to the 1 over 1 plus 1 over n. The 1 over n gets to go to 0, and you're left with e to the 1, which is e. So this sequence definitely converges. The limit as n goes to infinity of 1 plus 1 over n to the n is e.
Exactly.